Chapter 7, Transformer Relays. In this chapter, we're going to look at a various assortments of relays, both old and new. We're not going to spend a lot of time on the older installations, although you will find out there that they're still existing a lot of the older type relays because they're still functioning and still working fine and they still protect the transformer. However, we are also going to show you some relatively new transformer relays that are called IEDs, or the Intelligent Electrical Devices, that are basically computers that work extremely fast and provide a multiple of functions for protecting the transformers. We're also going to look at the oil flow protection, the Buchholz relay, towards the end of this chapter, which is used in most of the oil immersed transformers that are protected in today's protection schemes. This is an example of a three-phase or a three-element restraint differential relay. It's the SIA, or Brown Boveri, what it was when it first came out, D21SE, used to protect a two-winding transformer. It's definitely old school, but there's still a lot of them in existence today, so we will have a quick look at one of them right now. I've highlighted here what is would be considered the red phase operating and restraint coils for this relay, being fed with CT secondaries from the high side and the low side of the transformer. This shows the white phase operating and restraint coils being fed from the high side and the low side of the transformer, and this is the operating and restraint coils for the high voltage blue phase side of the transformer and the blue phase low voltage side of the transformer. Each of these operating coils will pick up a high speed contact that is designed to bring in the 110 or up to 240 volt DC control tripping mechanism for any breakers that would be required to isolate the transformer, and this will pick up an auxiliary relay with multiple contact outputs. It's simple and effective and carries out the function of a restraint differential relay. An intelligent electronic device, an IED, is a term used in the electrical power industry to describe microprocessor-based controllers for power system equipment. IEDs receive data from sensors and power equipment and can issue control commands such as tripping circuit breakers if they sense voltage currents or frequency anomalies, or raise and lower voltage levels in order to maintain the desired level. Included in the realms of IEDs are the modern protective relaying devices. Some recent IEDs are designed to support the IEC 61850 standard for substation automation, which provides interoperability and advanced communications capabilities. In utilities and industrial electrical power transmission and distribution systems, a digital protective relay is a computer-based system with software-based protection algorithms for the detection of electrical faults. Such relays are also termed as microprocessor type protective relays. They are functional replacements for the electromechanical protective type relays and may include many protection functions in one unit, as well as providing metering, communications, and self-testing functions. The digital numeric relay was invented by Edmund O. Schweitzer in the early 1980s. SEL, Arriva, and ABB groups were early forerunners, making some of the early market advances in the arena. But the arena has become crowded today with many manufacturers. In transmission line and generator protection, by the mid-1990s, the digital relay had nearly replaced the solid state and electrical mechanical relays in new construction. In distribution applications, the replacement by the digital relay proceeded a bit more slowly. While a great majority of the feeder relays in new applications today are digital, the solid-state relay still sees some use where simplicity of application allows for simpler relays, which allows one to avoid the complexity of digital relays. The progress and enhancement of these relay changes happens continually, and as such, the following examples have already been improved and additions made. However, the basics are still there, and even though newer versions are available, these examples will give a good idea of what is out there and what has happened in the way of IEDs for transformer protection today. Transformer differential protection relays in use today are more advanced and usually part of a multifunctional relay, so they are often referred to as transformer management relays. The relays are microprocessor based and are commonly referred to as intelligent electronic devices, or IEDs. Examples of these transformer management relays that we'll look at are the GE Multilin SR745, the Siemens 7U T51, and the MyCom P632. Now, these are only three of a multitude of relays that are out there on the market, and certainly internationally you'll find even more. However, these ones are good representation of what is out there today, and with technology changing as it does, these devices are changing very rapidly in themselves. However, if we look at these three samples, they'll give us a good idea of what IED type relays function as and what they're capable of doing out there in the way of transformer protection. Compensation for the transformer primary tap changer is also accounted for when applying relay set points. Harmonic restraint is provided and addresses the problem of false tripping for magnetizing inrush current during transformer energization. The relay settings are entered using application software run from a computer, usually a laptop, that's brought into the field. In general, you can create a new relay setting files from scratch, or you can modify existing settings and send them to another relay. Let's take a closer look at one of these relays, and we're going to start out with the GE Multilin SR745. The 745 transformer protection system is a full-featured transformer protection relay suitable for applications on small, medium, and large power transformers. The 745 can be applied to 2-winding and 3-winding transformers. Multiple current and voltage inputs are used to provide primary protection, control, and backup protection of transformers, including current differential, restricted ground fault neutral, ground overcurrent, overfluxing, and on-load tap changer compensation. The 745 also includes analog inputs and outputs, while incorporating advanced features such as transformer loss of life monitoring. For protection and control, the 745 has variable dual slope percentage differential protection, magnetizing inrush and overexcitation blocking, phase and ground overcurrent elements, adaptive time overcurrent using flex curve elements, underfrequency and overfrequency protection, frequency rate of change detection, overexcitation protection, restricted ground fault protection, and transformer overload protection. This relay, as well as most modern IEDs, come with communication capabilities that include the network interfacing RS-232 and RS-485 and RS-422 ports. It has an Ethernet port for sample rates up to 10 megabits per second. It uses multiple protocols: Modbus, RTU, Modbus, RTU, TCP, IP, DNP, and several others. Remote communications to a DAX or a SCADA or a PLC type system. And it's designed to allow simultaneous communication via all ports. Along with the protection and control features, this package also includes metering of current, voltage, sequence components per winding, power, and energy. It also tracks third harmonic distortion and the other harmonics up to the 21st. It is also an events recorder. It will also track the tap positions of a on-load tap changer transformer up to 50 tap positions. It will also record the ambient temperature using an analog input, and it also has analog transducer inputs for other functions. It also has a built-in oscillograph and data logger to track any events that need to be looked at after the fact. This relay has its own software. It's trademark registered, called InterVista software, that includes sophisticated software for configuration and commissioning. It's got a graphical logic designer with the logic monitor that simplifies designing and testing procedures. It has documenting software for tracking and archiving information, and it's easily integrated data of the 745 into new and existing monitor and control systems that are being developed out there. This is the functional diagram for the relay. It may appear a little bit confusing because each one of the function numbers associated with one of the individual three windings of the power transformer are prefixed with with a 1, 2, or a 3, depending on the winding that's associated with. For example, winding 1, the prefix on the functional numbers is 1. For winding 2, the prefix number is 2. And for winding 3, the prefix number is 3. So if you just remove those winding numbers, it becomes a little bit more obvious. The standard functional numbers are as listed here on the diagram. As you can see, it pretty well covers the entire spectrum of protection that's required for the transformer and then some. The 745 offers percent differential protection and features the equivalent of 3 single-phase differential current relays. Each has dual slope percent differential with second and or fifth harmonic restraint to protect against maloperation due to magnetizing inrush current during transformer energization and overexcitation. Each differential element has a programmable dual slope percentage restraint with adjustable slope break points. The 745 can be used to provide backup protection for transformer and adjacent power system equipment. Instantaneous overcurrent elements can be used to fast clear a severe internal fault or external through faults. Timed overcurrent protection elements per winding allow to coordinate with adjacent protected zones and act as a backup protection. Timed overcurrent protection functions are provided for phase and ground currents. A variety of standard time current curves and defined times are provided. Flex curves to coordinate with the adjacent protections, including fuses, as well as transformer damage curves and thermal damage curves for downstream equipment. Additional features for the 745 include negative sequence overcurrent. For delta Y impedance grounded transformers, overcurrent protection is particularly difficult to set. A negative sequence-based overcurrent element provides the required sensitivity. Dynamic CT ratio mismatch correction accounts for various variations in on-load tap changer positions. Tap positions are monitored and CT ratios are corrected accordingly automatically. For overcurrent and under frequency protection, the 745 calculates and maintains a running average of the system frequency and the frequency rate of change. 2 under frequency and 4 rate of change elements are provided to implement traditional and advanced load shedding schemes. Additionally, an over frequency element can be used to trigger a generator ramp down. Analog inputs, which are optional, include 7 transducer output channels allowing individually programmed outputs for ranges of 0 to 1 milliamp, 0 to 5 milliamps, 1 to 10 milliamps, 0 to 20 milliamps, and 4 to 20 milliamp. Channels are assigned to any measured parameter. All feed-in CTs are connected in a Y configuration for simplicity. Then all phases and magnitude corrections, as well as zero sequence current compensations, are performed automatically based on a choice of over 100 transformer types. The loss of life feature provides an estimate of how much the transformer's total installation life has elapsed based on IEEE standards guide for loading mineral oil immersed transformers and guide for loading dry type distribution and power transformers. Now let's look at the Siemens 7UT513. Some of the features of the Siemens 7UT513 include short circuit protection for 2 and 3 winding transformers, restraint during inrush, overexcitation, and CT saturation, short circuit protection for generators and motors, overload protection with thermal characteristics, 2-stage definite timed inverse and timed overcurrent protection, a restricted earth fault protection, a definite timed overcurrent protection, and direct injection of 2 external open commands. It also features a real-time clock and permanently stored operational and fault indicators in the event of auxiliary voltage failure. Substation control interface has also a commissioning aid for setting up new installations, and it is self-monitoring for internal faults. The 7UT51 can be accessed using the DIGSI operating program on a compatible PC front connected to the relay, or the substation control interface can be a fiber optic interface or a standard substation control system interface. Alternatively, this can also be an isolated interface using RS-232C. With the Siemens 7UT513 relay, all CT inputs to the relay are connected in Y, regardless of the power transformer winding configurations and secondary phase shifts. This is because the vector group compensation is accomplished mathematically within the relay itself. Matching of the CT ratios between the primary and secondary power transformer windings is accomplished within the relay settings. The actual CT taps should be selected to produce approximately the same secondary relay current. The relay has 3 main sets of 3-phase CT inputs and a capability of having 2 additional single-phase neutral CT inputs. The user defines which windings are referenced to the primary and secondary windings of the transformer. The single-phase inputs are used for restricted ground fault and ground overcurrent protections. The relay contains 2 independent thermal overcurrent elements that can be associated to any of the 3-phase CT inputs. These elements model the actual thermal behavior of the protected windings. In addition to the transformer protection, the 7U T513 is designed for application on bus differential protected zones. The relay has various techniques to recognize CT saturation. This relay also has 5 discrete binary inputs that are used to bring the status of external physical contacts into the relay. The relay contains an internal lithium battery that is used to maintain the state of alarm indications and a real-time clock and calendar through a DC supply interruption, if indeed it happens. This relay has fast clearance for heavy internal transformer faults. It also has a restraint of inrush current, recognizing second harmonics. It's restraint against overfluxing with a choice of third or fifth harmonic recognition. Additional restraint for external faults with current transformer saturation. And the differential protection function can be externally blocked if required. And just out of interest, this is how the Siemens 7UT513 is connected to the system. The MyCom relay is the last one, which we'll look at very quickly. The P63 series provides high-speed tripping 3-system differential protections using a triple slope characteristic and 2 high-set differential elements in combination with transformer inrush restraint, overfluxing restraint, and through stabilization. Amplitude and vector group matching is done just by entering the nominal values of the transformer windings and the associated CTs. It has numerous integrated communication protocols to allow easily interfacing to almost any kind of substation control or SCADA system. The integrated protection interface of the InterMyCom provides direct end-to-end communications between 2 protection devices. The following functions are generally available on all P63 series relays. Parameter subset selection, 4 alternative setting groups, metering, operating data recording, overload recording and overload data acquisition, and fault recording of all CT and VT inputs and binary events. And these are the MyCom's P632 functions. Protection-wise, it has differential protection, restricted earth fault protection. It has definite time overcurrent protection, as well as inverse time overcurrent protection. It has thermal overload protection, over and under voltage protection, over and under frequency protection, over excitation protection, and it has also capability of using or having circuit breaker failure protection built into it as well. As well, we have current transformer supervision, measuring circuit monitoring, limited value monitoring, programmable logic functions. They have measuring units for phase currents and residual currents and voltages, and several other options, including the communication interfaces that are standard that are out there, and it is also capable of interlocking with the IEC's 61850 interface. Not necessarily going into it in detail, but this is the functional diagram showing the functionality for all of the P63 series monitoring relays. This is the tripping characteristic of the differential protection, which has two knees. The first knee is dependent on the setting of the basic threshold value, which is indicated as ID in the diagram. The MyCom's P63 series differential protection devices are provided with a saturation discriminator that allow for such things as the startup of directly switched asynchronous motors that could cause transient transformer saturation. Restraint under inrush conditions is based on the presence of second harmonic components in the differential currents. For restraint under overfluxing conditions, the ratio of the fifth harmonic to the fundamental wave for the differential current of the measuring system serves as the criterion. Zero sequence filtering may be deactivated separately for each winding in the case of an operational grounding within the protected zone. Information exchange is done via the local control panel, the PC interface, and two optional communication interfaces. The first communication interface has a settable protocols conforming to the standard Modbus and courier connections and is intended for integration with substation control systems. The second communication interface is intended for central settings or remote access. Clock synchronization can be achieved using one of these protocols or using a standard external input signal. So this has been a very brief look at three examples of the modern type IED relays that are out there. It was certainly not intended to fully cover all of the aspects of the relays. That would take a lot longer to do. And it certainly wasn't intended to be a sales pitch for any one of the three manufacturers. It was intended solely for a quick glance at what is out there and what is the capability of these relays in today's day and age. The last protection device to be discussed in this chapter is more mechanical than electrical. At least the initiating variables, pressure and flow, are measured mechanically. This relay measures the rate and volume of gas accumulation in an oil-immersed transformer. It was developed by Max Buchholz in 1921 and since has been known as the Buchholz relay, which has been applied to large power transformers since about 1940. It has been slightly modified over the years, but essentially the basic principle of operation has remained unaltered. The Buchholz relay is located in the oil line that connects the conservator tank and the main transformer body. This position of the relay above the main tank will accumulate any and all gases that are formed and rise in the transformer. Also, any pressure surges that occur will pass through the oil connection line on the way to the conservator tank. The Buchholz relay usually has two elements that monitor, number one, gas accumulation, which is made up of a float and some kind of position activated switch. In this case, it shows a mercury switch, which in the more eco-friendly designs of today can be possibly a reed relay acted upon by a moving magnet. The second element measures gas pressure change, which is made up of a moving diaphragm and again some kind of position activated switch, a mercury switch or the more eco-friendly reed relay. For the time being and for simplicity, let's assume that the mercury switch is being used in both cases. Under normal conditions, there is little or no gas in the Buchholz relay, and the float keeps the mercury switch open. On a slow accumulation of gas, due perhaps to slight overload, gas is produced by decomposition of the insulating material as well as the oil. These gases will slowly rise in the transformer and accumulate in the top of the relay. As more and more of these gas bubbles collect, they will force the oil level down in the relay. The float switch in the relay will close and initiate an alarm signal. Depending on the design of the Buchholz relays, there could be a second float, and it will detect, or is designed to detect, slow oil leaks in the oil of the transformer. And if the oil level drops too low, and in this case, it would initiate a trip of the transformer. If an arc forms, gas accumulation is rapid and oil flows rapidly into the conservator tank. This flow of oil operates a switch attached to a vane located in the path of the moving oil. This switch normally will operate a circuit breaker to isolate the apparatus before the fault causes additional damage. Buchholz relays have a test port to allow the accumulated gases to be withdrawn for testing. Flammable gases found in the relay indicate some internal fault such as overheating or arcing, whereas air found in the relay may only indicate low oil level or a leak. Dissolved gas analysis, or DGA, is the study of dissolved gases in transformer oil. Insulating materials within transformers and electrical equipment break down to liberate gases within the unit. The distribution of these gases can be related to the type of electrical fault, and the rate of gas generation can indicate the severity of the fault. The identity of the gases being generated by particular units can be very useful, and this information is useful in the preventive maintenance program for the transformer. The collection and analysis of gases in an oil insulated transformer has been done as early as 1928. Many years of empirical and theoretical study have gone into the analysis of transformer fault gases. DGA usually consists of sampling the oil and sending the sample to a laboratory for analysis. Mobile DGA units can be transported and used on site as well. Some units can be directly connected to the transformer. Online monitoring of electrical equipment is an integral part of some of the transformers. Transformer oil is used to cool and insulate the internal components of a transformer. Because it bathes every internal component, the oil contains a great deal of diagnostic information. Just as blood tests provide the doctor with a wealth of information about the health of a patient, a sample of transformer oil can tell a great deal about the condition of the transformer. The oil analysis is broken into two parts. Physical, electrical, and chemical tests can evaluate oil for indicators of dielectric insulation breakdown, power factor, interfacial tension, and acidity and color. Dissolved gas analysis, or DGA, looks for certain gas quantities and combinations that can determine the likely failure mode. Here are some of the gases that could be found dissolved in the transformer oil and their possible causes to be prevented. Hydrogen indicates partial discharge, or corona, inside the transformer. Methane presence indicates overheating, and acetylene would indicate arcing presence inside the transformer. Ethylene would indicate the most likely failure to be in localized overheating, where ethane would indicate a general overheating of the unit. Carbon monoxide indicates cellulose overheating, which would be the wrapping insulation on the windings itself could be breaking down. And carbon dioxide would indicate that the oil and or cellulose would be overheating. The ability of insulating oil analysis provides an early warning sign of a problem condition and is dependent on the quality of the oil sample that is sent to the lab. A sampling point on any equipment should be identified and clearly labeled. The same location should be used each time a sample is collected to ensure representative conditions are tested. This point should be located in a place where a live oil sample is active rather than in an area where the oil is static. Fluids with specific gravity greater than 1 should be sampled from the top because free water will float. For fluids with specific gravity less than 1, such as mineral-based transformer oil, synthetic fluids, or silicon oils, the sample should be taken at the bottom, since water will tend to drop to the bottom of these fluids. There are a number of environmental variables such as temperature, precipitation, etc., to consider before collecting a sample. The ideal situation for collecting a sample from an electrical apparatus is 90 degrees Fahrenheit or 35 degrees Celsius or higher. 0% humidity and no wind would be very helpful as well. Cold conditions or conditions where relative humidity is in excess of 70% should be avoided, as this will increase the moisture in the sample. Collecting a sample during windy condition is also not recommended because of dust and debris that could enter the sample easily and disrupt accurate particulate counts. If sampling the oil is unavoidable when the outside temperatures are at or below 32 degrees Fahrenheit or 0 degrees Celsius, it should not be tested for water content or any properties that are affected by water, such as dielectric breakdown voltage. For dissolved gas analysis, an elaborate procedure must be followed, including the use of glass syringes, with strict adherence to sampling protocol to ensure that the concentration of dissolved gases is not influenced in any way by the sampling procedure. And this ends Chapter 7.